Hello everyone, it's your boy DJ Structures. Today's video we're going to be dealing with frames. We're going to understand what we mean by frames, then we start to solve frames straight. So what do I mean by frames? As someone who is familiar with design software like Start Pro, Structure, I've come to see frames. Before I just think of these things as just schoolwork, but I've come to see it as, wow, this is a column, wow, this is a beam, that is a vertical, the column, the horizontal, the beams. Do you get? And in fact, the beams can be slanted also, so your frame can also be slanted. But here in most of the schoolwork, we're going to be dealing with 2D frames, 2-dimensional frames, that is planar frames, frames like this, frames that you can just see in a 2-dimensional manner, frames like this, 2-dimensional, they are just saying 2-dimensional. So we'll be dealing with that. This is 2D, and of course something like this is 3D. Frames like this, frames like this. So now we should also know that when we ask whether a frame is statically determinate, we are not just asking is it statically determinate externally or is it statically determinate internally. We're asking that, okay, is this statically determinate? When you hear that, I'm asking you, is it determinate externally and internally or not? That is just what I'm asking. Why am I asking so? Why am I combining external and internal? Well, the truth is that when you are dealing with frames, we are not just dealing with axial loads, which is as that of the trusses, but we are dealing with also shear forces, and we are dealing with bending moments. These are all these three are internal forces. Now, we need to find internal forces, which are the bending moments, like I just mentioned, the shear force and the axial loads. Those are the internal forces. We need to find out them. And we also need to find out the external support reactions, which are the external forces. So in essence, we have two. We have external forces and we have internal forces. So anytime I ask you, is this frame statically determinate or not? You reply intelligently by saying it is statically determinate externally and internally, or it is statically indeterminate externally and internally. So we can now proceed from this stage. I think I'll just leave off. It's now erasing fast. Sorry about this. Yes, so let's get started. Now let's solve this frame structure. Mind you, the reference I'm using is Aslam Kasimali. .6 kilonewton per meter. Let's say this is 25 kilonewton. This is 10 meters. This is 10 meters. And from here to here, let's give it 15 meters. Let's say this is an imaginary line, just denotes vertical consistencies. You get 10 meters, 10 meters, 10, 10. So the first thing is to know whether it is statically determinate externally or internally. And the equation to use is this. I'm sorry about that. Excuse me. So this equation tells us whether it is statically determinate externally or internally. This M represents the number of members you have. R represents your reaction forces present. J represents your joints, basically, or your joints. NER represents whether you have, that is the equation of condition present. The amount of equation, the number of equation of conditions present. For instance, when you see an internal hinge, it has just one equation of condition. So you NER for that would be 1. But if your structure has 2 internal hinges, it means that 1 plus 1, which is 2, you'll be putting NER as 2. However, for internal rollers, if you find a frame structure with internal rollers, you put for just one internal roller, it has 2 equation of conditions. That is for 2, we have 2 plus 2, which is 4 equation of conditions. So that is just how to go about it. Now, if D is equals to 0, it means that it is statically, your frame is statically determinate, externally and internally. That is, we can find and compute for the bending moment, the shear forces, the axial loads, and the support reactions. Statically determinate, externally and internally. If D is less than 0, it is unstable. That is, it has more than is enough to solve for that. It has more than its, maybe the unknowns are less than the amount of equations required to solve for them. So now when D is greater than 0, you have an indeterminate, statically indeterminate externally and internally. So that's just the key thing. And internally. So now, reproducing this, means so I'll copy it, paste it here. So the first step, let me erase this so I can see it well. The first step is to solve for the support reactions. That's the first step. Solve for the support reactions. So we have, of course, you draw your free body diagram. Then directions. Let's call this AY. Let's call this reaction AX, and let's call this M. That's the first step. So, no, we haven't even computed for whether it is determinate or not. So, if you use this method, what I just said, you'll find out that D is equals to 0. What do I mean? You see, D is equals to 3 times how many members? 3 times 2 members, plus R. We have 3 reactions. I mean, from this A, we have 3 reactions. Minus 3, we have how many joints? We have 1, 2, 3 joints. Now NER is 0 here, so plus 0 or minus 0, anyone. So you'll find out that this is going to be 0. Do you get? So erasing this. No. Yes. So now we move to the next step, which is to get the equilibrium equation, which is to get the support reactions using the equilibrium, applying the equilibrium equations to the overall structure generally, not splitting the structure. So to do this, we apply the equilibrium equations to the structure. We say that, okay, looking at this, to apply the equilibrium equations to this structure, I say first thing, summation Fy is equals to 0. I basically think of it as my upward is equals to my downward. So by this, I can say that AY, which is coming from beneath from this support reaction upward, is equals to downward, is equals to 1.6 times 15, which is equals to 24 kilonewtons. Similarly, summation Fx, apply my equilibrium equations, equals to 0. I have 25 going in this direction, and I have AX also going in this direction. Those are the two horizontal force components I have. So 25 plus AX is equals to 0. That is what I have, is equals to 0. So it means that AX is equals to minus 25 kilonewtons. So one thing that you must understand is that your equilibrium equations would give you your corrected sense. All what we've assumed is can change. So we assumed all this direction. So it means that my AX is going to be changing the direction, but I'll change it later. For now, I will stick with using this negative sign in any of the computations I do before I change it. So the next thing is to apply the third equilibrium equation, summation MA, let's use at point A is equal to 0. So looking at the structure, applying the moment at A to be 0, let's think, the way I think of it is that let's imagine a ball is here. Let's imagine a ball is here. So at A, the things that will act would be a force coming from this UDL. Another force coming from here would act on the ball, and that is those are the only forces that will be acting on the ball. So for the UDL, I will be having 1.6, converting the UDL first to a point load. 1.6 times 15 will convert my UDL to a point load. Exactly. Then times 15 over 2, which is the distance from here to here. Because I mean, after converting to a point load, I can now multiply it by distance, perpendicular distance. I mean, this is the perpendicular distance to this. So 15 over 2. So I'll be having 1.6 times 15 square over 2. Sorry. .6 times 15 square over 2 plus, now this is going to be, now this blue stuff will be rotating it in a clockwise manner. Also, this 25 force, which is acting like this, will also rotate this ball in a clockwise manner. That is why it is in the same place with the one for the UDL. So 225 times perpendicular distance 10 will be all equals to MA. Now that is, if you notice, I normally do either upward is equals to downward, clockwise is equals to anti-clockwise. I don't have time to check to use sign convention. So you just do it and you get your same answer. So clockwise, all this now, all these blue forces, blue arrows, will now be equals to anti-clockwise. The only anti-clockwise I see on A is on this structure is the anti-clockwise that came from this moment. But you may be thinking, Deji, how come? Are we going to apply this moment? I mean, it's moment at A. I mean, there's no perpendicular distance. Well, it's already a moment already. Had it been it was a force there, you're not going to be multiplying by any distance because that is the point already. There's no distance there. Your distance is 0. But now it is a moment. The moment has been multiplied by distance already. It's already a couple. So you can just take into account. So equals to MA. Remember everything at point A. So moment is already applied at A. So which is coming from the fixed support that was there. So MA. So MA is equals to 430 kilonewton meters. Sorry. Now, we've seen that the direction for some change, so we have to give it a corrected direction. I mean, AX changed, so we have to change the structure so that it will be so convenient for us. So I copy it and I paste it here again. Sorry. So this is the structure, but now I have to change some things. The direction of that I zoomed. So I decompose this fixed structure, and I have, of course, my AY was the same, was consistent. My moment was also consistent, which was 430. But the only thing that was not consistent was AX. AX is supposed to be in this direction, 24. So the next thing after correcting the sense of my reaction forces is to decompose the structure. And I decompose the structure by splitting the structure, by splitting it. So I split the structure into a column and a beam. A column and a beam. I mean, you can see a column and a beam. Now, I represent my forces again. 24, 430, 25, 25, 10, 10. Now, decomposing the structure, I'll be left in this manner. So it's 1.6, 15. I'll be left in this manner. The remaining things, now I'm teaching for people that need to be fast in their exams. This process is a long process. So when you see that in your question, no force is applied on the joints like this, or maybe maybe in this way. When you see that there's no force applied on the joints, maybe this is a force, maybe we're talking about joint B now, but maybe there's no now force, I'm erasing the force now, then you can continue, you can just go on the way I'm proceeding. That is, you don't need to show the joint. You don't need to show the joint. That is why I'm not showing, because there's no force acting on this connecting joint. So I don't need to show the joint. But at the beam there was a force acting, I need to show, that force that is acting, it must not be on this particular beam. So it must not be on this column. Okay, let me come again, I'm sorry. Let's say a force is acting here. You might think that this force is acting on this particular column or on this particular beam. Don't think of it like that. It will confuse you. So to avoid that thought, just apply that force to that joint alone. Put the joint and apply that force. Then draw the free body diagrams of all your stuffs. But luckily for us, no force was applied on the joint. So we can proceed. So the next thing is to have, due to Newton's law, when you are assuming directions, all this now, all this, we don't have a support here. So all this now are internal forces. So we need to assume direction. And it will be so smart of you to assume in your direction in an opposite manner to what you have in your structure. So, I have one vertical up, so I need to have another vertical going down. BYBA, BXBA, and also a moment. We're having a moment there because it's a rigid connection. a rigid connection, you can transfer moments. BBA. Now, similarly, applying Newton's law, we can see that BY, we can put another arrow here because it is counteracting this one. Like, we just need to be smart in assuming. Now, we will now say BY. Now, this is B and also in the Y direction, but now it will be BC because this is member B and C. You get? So this will now be in this direction, BX, BC, and also a moment which is acting in the opposite direction to the one at MBBA at B, but for BA, so we're having an opposite direction of moment, which is MBBC. So the next step after doing this is to now draw a free body diagram. A demarcation is to draw a free body diagram of all my structure. Or what am I saying? Is to apply equilibrium equation to all the individual splitted parts. So applying my equilibrium equation to part 1, that is member AB. This is A, B. Applying equilibrium equation, I'll be having that applying summation Fy is equal to 0. I'll be having that BYBC is equals to, BYBA is equals to 24. I mean, upward is equals to downward. Can you see? BYBC, up, downward is equals to upward also, equals to 24. Similarly, I'll be solving summation Fx. Now, summation Fx is equal to 0, right is equal to left. BXBA plus 25 is equals to 25. So basically, BXBA would be 0 kilonewtons. And now the last one, the last equilibrium equation, summation MBBC. When summation MB is equal to 0, we're finding moments at B. Or no? I'm sorry, summation. Let's do summation MA is equal to 0. We can, as long as this moment is member AB, we can either find moments at this point at A, or we can find moments at point B. So, but I always go with finding moment at A. It makes it easier for me. Finding moment at A. If finding my moment at A, I will assume a ball is here. Then 25 would give it an anti-clockwise rotation. 25 can't affect it because there's no distance. So the only thing at A that can affect it is that moment, which will give it an anti-clockwise rotation. 430 anti-clockwise. The remaining would be clockwise. 430 is equals to, that's anti-clockwise equals to clockwise, which is 25 times 10. BXBA is 0, so nothing, plus MBBA. So we can say that MBBA is equals to 430 minus 250, which is equals to 160 kilonewtons meter. Thank God it wasn't negative, if not, would have changed it. So the next thing is to now apply our equilibrium equation to joint B. So now, that is why we said that this method can be fast. Had it been we were drawing joint B, we don't need to draw joint B here because no force is acting at that intersecting point. Although when solving, we need to also compute for joint B. Once again, here, because there's no force acting at that intersecting point, we don't need to draw for it, but so that it, yes, we don't need to draw for it, but when we are solving, we need to solve for it. So joint B. Summation Fy is equals to 0. Applying summation Fy to it, we'll be having, applying summation Fy to joint B. I mean, this is joint B, these two people here. Looking at our structure, this is B, just look at it, and come here, then at joint B, summation Fy to be 0, you can say, you will see that your BYBC, your downward or your upward is equal to your BYBA, which will give you 24 kilonewtons. Similarly, the summation Fx is 0 is equal to 0, but we can't solve for summation Fx. We don't have to waste our time because Bxb is already 0. The point of solving for applying equilibrium equation to joints is to transfer moments from BA to BC, from this point to this point. So since there's nothing in BXBA, there's no point of applying equilibrium equations for that transfer. So now we move to summation, the summation of moments, since there's no summation of forces in x direction at B is equal to 0 now. So looking at this, once again, forces can't act because there's no distance between them, but moments would act. Anytime you are finding the equilibrium equation for a joint, just make sure that it is moments you are dealing with. So your moments, this moment here is in a clockwise direction. This moment here is in the anti-clockwise direction. And once again, clockwise is equal to anti-clockwise, your normal physics. So MBBA is equals to MBBC, which is equals to 180 kilonewtons meter. So now that we've done for joint B, we've established that BYBA is equals to 24 kilonewtons. MBBC is equals to 180 kilonewton meters. Now the next thing is to compute for our shear force and bending moment. We'll do that in the next video, guys.